Hello, seniors. Welcome back. We are continuing talking about probability for our statistics portion of this year. We're going to do a quick little recap over what we talked about last time and then jump into frequency tables. So, last time we talked about three important pieces that show up in probability. So, these are independent events, mutually exclusive events, and when we have probability of and an or event. So, independent events essentially are events that are do not affect each other. So they, for example, an example of independent events would be like rolling a dice and flipping a coin. You can roll your dice, you can flip your coin, but they're not going to affect each other. They are each separate results, and they won't necessarily, depending on whether you get a heads or a tails, won't necessarily affect each other. Now, when we're finding the probability of independent events, your probability of or A and B is how we write it. So probability of both of these certain events happening, like the probability of getting a heads and the probability of getting a 6 on a 6-sided dice, is going to be equal to the probability of the first event times the probability of the second event. So you just take the two events and you multiply them together, and that's how you get your probability. So probability of the first one times probability of the second one, because it's just the probability of this one happening and the probability of that one happening. So you just multiply them together. That's how you guys get your probability because they don't affect each other. Now, mutually exclusive events is not necessarily the same as independent events, and they're not necessarily opposites either. Mutually exclusive events cannot happen at the same time. So, for an example of mutually exclusive events would be, for example, rolling a 2 and a 5 on the same dice. It's impossible to get a 2 and a 5. You're either going to get a 2 or you're going to get a 5 or you're going to get some other number, but you can't get both of them at the same time. So the probability of getting probability of getting two mutually exclusive events happening at the same time is 0 because it's impossible. It's not going to happen. So your probability of getting like your 2 and your 5 has a probability of 0 or possibility of 0. Now, the last thing is probability of A or B. This is the probability of getting either event happening. So the probability of getting your first event or probability of getting your second event. You don't care which one happens as long as either of them happen. Now, what we have to do for this is we take the probability of A plus the probability of B. You add the two probabilities together. So whatever the probability of first event is plus probability of second event. And then we have to subtract the overlap. The reason we have to subtract the overlap of the two is because you're counting that overlap in both A and B. So we need to subtract it at least once so it's only counted once. So it's only counted at A or it's only counted at B, vice versa. Now, depending on whether these are mutually exclusive or independent events might change how you have to calculate this part, or it might be something completely different if it's a dependent event or non-mutually exclusive. But that is our probability of A or B that we worked with. So jumping into today, we're talking about frequency tables. So this is using two-way frequency tables to help us calculate probabilities. So what effect, if any, does taking a driver's education class have on your ability to pass your driver's test? So if we look at this two-way frequency table, we have the number of students who took the class is a total of 39, with 32 of them passing and 7 of them failing. The number who did not take the class is 41, with 18 of them passing and 23 of them failing. The total number of students who passed, if we look vertically, is 50 students. 32 of them took the class, 18 did not. The number of students who failed would be 7 who took the class, 23 failed and did not take the class, for a total of 30 students. And a total of 80 students altogether taking class, passing, failing, whatever, a total of 80 students. So this is a two-way frequency table, and this helps us display different types of categories or different information about some of our data and helps us determine some probabilities. So can we determine if taking the driver's test or taking the driver's education class has any effect on your passing abilities? Well, if we look at it, we see that 32 or probability of passing for taking the test, probability of passing for those who took the test were 32 out of 39, which if we calculate that, 32 out of 39 gives us roughly 0.82% or 0.82, about 82%. Now, probability of passing when you didn't take it was only, so probability of passing if you didn't take it, probability of passing was equal to 18 out of 41 students did not take it and passed. So 18 out of 41, if we look at this, is 0.43, or roughly about 0.44. It's 0.439, so if we round up. So we can see that almost double your chances, or you almost doubled your chances when you took the class versus did not take the class, based off the probability. So two-way frequency tables are helpful for us to be able to identify different sorts of data and look at multiple variables at the same time. So the table shows student involvement at a local high school in extracurricular activities. What is the probability that a randomly selected student is female? So what is the probability that a randomly selected student is female? So what we need to look is we're looking for probability of female. So if we look at it, we have male students, female students, involved in activities, not involved in activities, and then their total. So if you look at female students, the probability of getting a female student in total, we have a total of 259 female students. So if we click this, total number of female students is 259. Out of a total of how many students, total students can you pick at this high school? Well, if we look at the totals, there's 516 total students. So 516. So 259 over 516, 259 divided by 516, it gives us a probability of 0.50. So 50%, just barely above 50%, if we look at the other decimals, is above is female students. So what about the probability that a student is not involved in activities? So if I randomly pick a student at this high school, what's the probability of them not being involved in activities? Well, I just need to look how many students are not involved in activities. The total of students that aren't involved in activities is 265. The probability of not involved equals 265 divided by the total number of students I could pick from, which is 516. I think the little, that's all right. So 265 divided by 516, 265 divided by 516 gives us a total probability of 0.51. So roughly just above 50% of our students, or 50% of the students picked in here, are not involved in activities. Let me shrink that a little bit. That's a little too small. Yeah, too big. Nope. I apologize. There we go. All right. Now, what is the probability of students? What is the probability that you randomly pick a female student that is not involved in activities? So I'm looking for the probability that the student is female and not involved. So I need to think, okay, how many students are not involved in activities? So I look, where's my overlap of female and not involved in activities? Is a total of 120 students are female and not involved. Divided that by my total number of students I can pick from, which is 516, and my randomly selected probability, 120 divided by 516, gives me 0.23. So roughly about 23% is the probability that I can randomly pick a student that's going to be female and not involved in an activity. So that's how we can use our two-way frequency tables. We can look for those overlaps. Typically, we're using those totals if you're looking for full groups, or you can look for those and statements, which are going to be any of those overlapping spots. So female not involved, male that is involved, female that is involved, male that's not involved. You can find those overlaps pretty easily with the two-way frequency table. All right. Okay. So the table at right shows the number of male and female students by grade level on prom committee. What is the probability that a randomly selected member of the committee is male who is a junior? So I'm looking for the overlap of male and junior. So if I look at my total prom committees, I have 3 students that are male and junior out of total 12 random students. So my probability of picking a male that is also a junior is going to be 3 out of 12, which is just 0.25. So 25% chance of getting a male that is a junior on that prom committee. Once again, pretty easy, not too hard. You're just looking for those overlaps in those cells. Now, the probability of an event will occur given that another event has already occurred or another piece of information is already known is called conditional probability. We write conditional probability of an event B given that event A has occurred as P, or probability equals B slash A. So this is read as the probability of event B given that event A has occurred. So probability of event B given event A. Now, So the given statement, so typically a given statement is always something that you're told ahead of time. So like what's the probability of randomly picking a student given, or what's the probability of randomly picking a student that has a 4.0 given that the student is a freshman? So I already know the student's a freshman. What's the probability of picking from 4.0? So essentially it narrows down our options based off this given. We're not randomly picking a student out of all of the classes. We're randomly picking a student out of some given group. So conditional probabilities, there's that extra condition added on that narrows down your options. So let's look at some options of this with two-way frequency. So the respondents of a poll were asked whether they were for, against, or had no opinion about a bill before a state legislator that would increase the minimum wage. What is the probability that a randomly selected person is over 60? So probability that a randomly selected person is over 60 years old, given that the person had no opinion on the bill. So we have two pieces of information. We're looking for what's the probability that person's over 60, given that they had no opinion. So for how we would write this, we would put probability. We're looking for the person is over 60, given, which is represented by that line, that's a given, that they had no opinion on the bill. Probability of 60, given that they have no opinion. So what we need to do is we know we're looking for the people that are over 60. So how many people are 60 that have no opinion? So we see our total. So we see, okay, we have our line 60s down here. We have 150 are for, 20 are against, 40 have no opinion. So we know the person already has no opinion. So we know our total number of people that we can select from is only going to be 210. Or sorry. So we know the person has no opinion. So we know our total number of people that we can select from is 100. There's only 100 people that have no opinion on this. Now, out of that 100, only 40 of them are 60. So our probability of getting our desired outcome of someone who's over 60, given that we know the person already has no opinion, is going to be 40 out of the 100 people that we know have no opinion. So 40 out of 100 is 0.40 is our probability. Let's look at one more example of that. All right, so we have, so it's the same idea, same table, I believe. Yeah, sorry, exact same table. Okay, so we have some couple different questions. So what's the probability that a randomly selected person is 35 or 30 through 45 years old, given that the person is in favor of the minimum wage bill? So we know the person is already in favor of, so we know they already have that information. Sorry, let me pause this really quick. All right, sorry about that. All right, so we're looking for what is the probability that a randomly selected person is 30 through 45 years old, given that the person is in favor of the minimum wage bill. So we're looking for the probability of 30 through 45. So I'll just say 30 for now. Given the person is in favor of the minimum wage bill. So in favor. All right, so we need to think, okay, how many people are how many people are 35 and through 40 that are in favor of the minimum wage bill? So if I look, okay, my 35 through 40 that are in favor of or for the bill is 200 total people. So I know my desired outcome is there's 200 total people. Then you think, okay, how many total people are there that are for the minimum wage bill? Because I know this person is already in favor of the bill. So the total number of people that are in favor of the bill is 780. So I'm selecting from that 780, and I'm hoping to get one of those 200 people, which equals 200 divided by 780 is 0.26, roughly 26%. All right, last question. What is the probability the randomly selected person is not 18 through 29, given that the person is in favor of the bill? Okay, so we're given a not statement, so that when we see that not there, we know it's going to be a complement essentially. So we're looking for the probability that a person is not 18 through 29, given that we know the person is in favor. So once again, we're looking for people who are in favor. So we're looking through those 780 people that we know are for the bill. Well, how many total people are not 18 through 29 out of that 780? Well, if we look at the total number of people that aren't 18 through 29, we have the 30s through 45s, the 46 through 60s, and the over 60s. So if we do 200 plus 120 plus 150, the total number of people who are for the bill that are not 18 through 29 is a total of 470 people. So there's 470 people who are not 18 through 29 who are for the bill out of the total number of people who we do know are for the bill or in favor of the bill, because that's our given statement, is at 780. So 470 divided by 780 gives us a final probability of 0.60, so roughly about 60%, with a little bit of decimal change on there. And so that is how we can use frequency tables to help us find conditional probability. So once again, conditional probability just gives us that other statement that sort of narrows down. So rather than looking out of the total people, I'm looking out based off of my certain conditions. So whether they're for a bill, against the bill, I know they're over 60 or something like that. I can use all that information to help narrow down instead of looking out of the 1,000 total people I have. So that's why two-way frequency tables are helpful with conditional probability. We'll look a little bit more about conditional probability tomorrow, or not tomorrow, whatever day, Tuesday next, whatever day we meet next after this. And then you're going to have a little activity after this where you're going to look at the Titanic and see if there's any conditions based off class and survivability on the Titanic. Let me know if you have any questions. Have a great rest of your day. Oh, sorry. Click the wrong button once again. This is the button.